Welcome viewers to the sixth lecture for the online series of lectures for the course of Algebraic Topology 1. In this lecture we are going to start homology theory. In order to do that we need to discuss a few background materials. Today's lecture is dedicated to this preparation of homology theory. In this lecture we are going to study the concepts of simplices and simplicial complexes. We'll also review basic aspects of free abelian groups. Okay, so let's get started with the definition of simplices and simplicial complexes. Given a set A0, A1, all the way up to AN of points of R to the big N, all right, which means that each of the elements in this set is an n-tuple. Okay, all right. This set is said to be geometrically independent if for any scalar Ti belonging to the set of real numbers, the equations, there are two equations to be satisfied. One is the sum of all the Ti's being 0, and the other one being the sum of all the Ti times Ai's are 0, is 0, I running from 0 to n. Okay, so these equalities will imply that the scalars are identically 0. Okay, so that's the only way one can satisfy equation 1. Okay, it is immediate from the previous discussion that a one point set A0 is always geometrically independent. Okay, so if you just have the singleton set, then there is only one scalar coming into play, and the first equation tells us that that scalar is identically equal to 0. Okay, and and well, everything becomes trivial then. Okay, all right, so a singleton set consisting of one point of r to the n is always geometrically independent. It can be shown that this set consisting of n plus 1 points in R to the big N is geometrically independent if and only if the following vectors in R to the big N, a1 minus a0, a2 minus a0, all the way up to an minus a0. Okay. So there are n vectors here, n vectors in R to the n. So if and only if these n vectors in R to the n are linearly independent. This way we explore the connection between geometric independence and linear independence. Okay, so this needs to be proved. Okay, so let's see how we can prove it, how we can prove this relationship between geometric independence and linear independence. Let us first prove that if the set a0 all the way up to an is geometrically independent, then the n vectors that we have written earlier, a1 minus a0, a2 minus a0, all the way up to an minus a0, these n vectors are linearly independent. This is what we need to prove. Okay. Now consider n scalars, that means n real numbers, ti, for I equal to 1, 2, all the way up to n, such that the sum of these expressions ti time ai minus a0 is equal to 0. We number this as equation number 2. Okay, so we choose ti's in the set of real numbers such that this expression is equal to the expression that is on the left side is equal to 0. Okay, we now have to show that if a geometric independence holds, then each of these scalars ti's are identically 0. Each of these scalars is identically 0. Then each of the real numbers ti's is 0. This is what we need to prove. Okay. All right. Now take this real number t0 such that the sum of these numbers is equal to 0. Okay. Okay, so such a t0 can always be found. Okay, such that t is 3 is satisfied. All right. Also, we have sum over I, where I runs from 0 to n, the sum of all these expressions Ti times Ai, can be decomposed into the sum of all these terms Ti times Ai, where I runs from 1 to n. So we separate the part corresponding to I equal to 0. Okay, we extract that part from this summation, and that gives us this guy plus T0 A0. Okay, and now it can this expression can be manipulated to to give us Ti times Ai minus A0. Okay, so we subtracted an additional thing here, and that's why we have to take the sum of that additional part from I equal to 1 to n, Ti plus T0 A0. Okay, so that we are good, right? So I need some room, and these then gives, okay, the left hand side is this expression, the sum over all Ti times Ai, where I runs from 0 to n is equal to this guy, right? Yes. Okay, so let me write this the first summand first. This is the sum over all i's from 1 to n, Ti times Ai minus A0, and then I just take the sum over all the i's from 0 to n instead of 1 to n. Okay, plus A0 times sum over all Ti's, where I runs from 0 to n. Okay, so we added an additional part here, and that needs to be subtracted, and that subtracted part cancels against this C0 times A0, so that we have nothing else left. Okay, so we number this equation as 3 prime. Okay, this was 3, this is 3 prime, and this guy is 0 by using 2 and 3. So if you don't remember 2 and 3, let me write 3 is already here. This is 3. Okay, 3 is here, and 2 was this. The sum of all the terms Ti times Ai minus A0, where I runs from 1 to n, is equal to 0. Okay, so if you plug in this expression here, this goes away. So does this, because of this equation number 3, and you end up with a 0. Okay, and that's equation number 4. Okay. Okay, good. Now, okay, let me erase this part. Now, since the set A0, A1, all the way up to AN is geometrically independent, okay, So 3 and 4, 3 was this, sum over ti is equal to 0, where you sum over all i's from 0 to n, and 3 was this is 3, right? And 2 was 2 was the sum over all i's from 0 to n of the following expression: ti times ai minus a0 is equal to 0. This was equation number 2. Okay, and so these two equations, well, okay, so since this set is a geometrically independent set, these two equations imply 3 and 4, well, this 3, okay, not 2, 3 and 4, this is 4, okay, this is equal to 0, okay. 3 and 4 together imply that all the corresponding scalars are identically 0, okay, from the definition of geometric independence. Okay, good. Now this is equation 2. Now since this holds and we have all these coefficients being identically 0, okay, meaning that here okay, it is actually from 1, okay, from 1 to n. All right, and since in equation number 2 all these scalars are identically 0, it means that these vectors a1 minus a0, a2 minus a0, all the way up to an minus a0, these n vectors are linearly independent. Okay, this is what we wanted to prove, right? Now let us try to prove the converse. Let us prove the converse. We assume that the vectors a1 minus a0, a2 minus a0, all the way up to an minus a0, these n vectors are linearly independent. Okay, now we have to prove that the set a0, a1, all the way up to an, this set of n plus 1 points is geometrically independent. Independent. That's what one needs to prove. Okay. Now consider scalars. Such that the following two equations hold. the sum over ti's as I runs from 0 to n is 0, and the sum over ti times ai as I runs from 0 to n is equal to 0, which we number as 5. Okay, so suppose that for n plus 1 scalars, number 5 is satisfied. Okay, now using equation number 3 prime, let me write it for you if you don't remember. Equation 3 prime was sum over sum over all i's from 0 to n of this expression ti times ai, and this was shown to be equal to the sum over all the terms ti times ai minus a0, where I runs from 1 to n, plus a0 times sum over all ti's, where I runs from 0 to n. Okay, this was our equation number 3 prime. Okay, good. So using this 3 prime, one writes this guy I equal to 0 to n ti ai is equal to, well, exactly, we are rewriting 3 prime. This is ti times ai minus a0, this one, plus a0 times ti as I runs from sum over ti as I runs from 0 to n. Okay, this is 3 prime, and using this equation and 5, one immediately concludes that sum over this goes away, right? Because this guy is 0. Sum over all ti's is identical equal to 0, so it goes away and we are left with this one, and since this is 0, this is also 0. So the sum of all the terms like ti times ai minus a0 is equal to 0. This is our equation number 6. Now, according to the hypothesis, these n vectors are linearly independent, right? And so the equality of the equality given by equation 6 then implies that all these scalars are identically 0. Since these vectors are linearly independent, we must have t1 equal to t2 all the way up to tn to be equal to 0. Okay, all right, and we know that the sum of all ti's is equal to 0, so t0 has to be 0 as well. Okay, so together this and this equation imply that t0 is equal to 0, so that we finally have all these scalars are identically 0, starting from t0, t1 all the way up to tn. Okay, okay, which means that the set a0, a1 all the way up to an is geometrically independent. Okay, this is what we need. So this is how we establish the relationship between geometric independence and linear independence. Now Let us get to the equation of a simplex and simplex. Okay, let me erase these things first. We are getting to a new concept called n simplex definition. Let this set of n plus 1 points in R to the big N, which is a geometrically independent set. So let this set be a geometrically independent set in R to the N. Okay, so all the each of these points is an n tuple. Okay, we define the n simplex. Okay, we denote the simplices with sigma, small sigma always. Okay, we define the n simplex sigma spanned by this this is n, meaning that there are n plus 1 points. Okay, so we define the n simplex sigma spanned by these n plus 1 points to be the set of all points x of R to the n, meaning that it's the set of all n tuples such that x can be written down as a linear combination of these n plus 1 points. Okay, with the scalars satisfying this constraint. We want the sum of all these scalars to be equal to 1. Okay, and each of these scalars is non-negative. Okay, the numbers TI's are uniquely determined by this given x by the point on the n simplex. Okay, and they have names. They have a certain name. They are called the barycentric coordinates. Barycentric coordinates of the point x. Okay, of the simplex sigma with respect to these n plus 1 points. With respect to this n plus 1 points, sorry, not n points. Okay, so the last point is a sub n, meaning that there are n plus 1 points. Okay, so these scalars are called barycentric coordinates of the point x of the simplex, of the n simplex sigma. Okay, all right, now we'll see some examples in low dimensions, some examples of n simplices in low dimensions. Okay, starting from the 0 simplex, which is of course a point example. Simplices in low dimensions. A zero simplex is a point. Okay, good. The one simplex spanned by, okay, a zero simplex is spanned by only a zero, okay, and a one simplex is spanned by 2 points. One simplex spanned by a0 and a1 consists of all points. Remember the general expression of the points of n simplices, n simplex sigma, okay, and x belongs to sigma, and x is written as the sum of all the expressions like ti, ai, where I runs from 0 to n, and where the scalars in this expression should satisfy this constraint, sum over all i's. Sum of all the ti's as I runs from 0 to n has to be equal to 1. Okay, so that's the general definition of an n simplex. Okay, so it reduces to the following expression for the case when n is equal to 1, right? So there are 2 points, a0 and a1. So x can be written down as if you just use this expression, it's just t0 a0 plus t1 a1, and we also want sum over t0 plus t1 is equal to 1. So we can combine these two equations to have x written by a single equation like this: x is equal to t times a0 plus 1 minus t times a1. Okay, which means that we don't have to write this equation separately. It's already implied in this single equation with t lying between 0 and 1. Okay, so this is the case when we have only 2 points in our set. Okay, so what does it mean? This is just the line segment joining a0 and a1. Okay, this is the parametric equation of a line segment joining a0 with a1. Okay. Good. So a zero simplex is a point, and a one simplex is a straight line. Now, what is a two simplex? We'll see that a two simplex is a triangle. The two simplex sigma spanned by 3 points a0, a1, a2 equals the triangle. By triangle, so it's important to note that by triangle we mean the interior of 3 lines joining the 3 vertices which are non-collinear. So these 3 points are non-collinear. They cannot lie on the same line. Okay, and so we can join these 3 vertices to form a triangle. Okay, so the interior of these 3 lines is called the triangle, this region. So the two simplex sigma spanned by these 3 points equals the triangle, which is nothing but the interior of the 3 lines joining the 3 vertices which are non-collinear. Collinear. Okay. Okay, so equals the triangle having these 3 points having these 3 points as vertices. So this can be seen in the following way. How do you find a triangle? Can be seen in the following way. Okay. So according to the general expression of a point lying in an n simplex is x equal to sum over all such expressions ti ai. Here I runs from 0 to 2 since we are dealing with a two simplex, right? N is equal to 2 in this case. Okay, so it means that we can write it as t0 a0 plus 1 minus t0 times t1 over 1 minus t0, so that 1 minus t0 cancels against 1 minus t0 from the top and from the bottom, and we end up with t1 a1 plus again 1 minus t0 times t2 over 1 minus t0. Again 1 minus t0 cancels from the bottom and the top, and we are left with t2a2. Okay, now this is written as 1 we can factor out 1 minus t0, and inside the square bracket we have t1 over lambda times a1 plus t2 over lambda times a2, with lambda being equal to 1 minus t0. Okay, good. So we number this as 7. Now from this equation 7, one finds that that a point P lying in the line segment joining these 2 points A0 and A1 is given by this expression, right? So this is the coordinate of, well, it is the case because T1 over lambda plus T2 over lambda is equal to 1, right? Because from the equation of the simplex we know that it's not just one equation, there is another constraint, and what was that constraint? That being the sum of all the ti's is equal to 1, right? I from 0 to 2 is equal to 1, and using this constraint here we see that it is exactly equal to 1, right? Because this is t1 plus t2 over lambda, right? And what is lambda? Lambda is 1 minus t0, and we know that this holds, right? Which is t0 plus t1 plus t2 is equal to 1. So t1 plus t2 is 1 minus t0. This is 1 minus t0, cancel again against each other, so that we just have 1. Okay, so the sum of these two scalars is 1. What does that mean? It means that it is this guy, what we have inside the square bracket is the coordinate of a point lying in the a line segment joining A0 and A1. Okay. Okay. Now consider this line segment joining. Sorry, I think I should have written it since we are dealing with A1 and A2. A0 have to be here. A0 has to be here, and this has to be A1, this has to be A2. Okay, so P is the point lying between lying in this line segment joining these 2 points A1 and A2. Is A1, this is A2. Good. And now what about our point lying in the line segment joining these 2 points A0 and P? Okay, that has to be T0 A0 plus 1 minus T0 times P, and P is coordinatized by this expression, right? So that this is nothing but T0 A0 plus 1 minus T0 times this expression, T1 over lambda times A1 plus T2 over lambda times A2. Okay, so this means that this is the expression, the final expression is the coordinate of a point lying in this region. Okay, good. So let me write the conclusion. Therefore, x equal to T0 A0 plus 1 minus T0. So that is the reason I'm leaving 1 minus T0 here. Instead of writing as lambda, I'm just writing it 1 minus T0. So that T0 plus 1 minus T0 is equal to 1 becomes manifest. All right. And inside the square bracket, I have T1 over lambda A1 plus T2 over lambda times A2. This represents a point in the triangular region formed by joining the vertices A0, A1 and A2. So let me draw the figure again for clarification. So we start with A1 and A2 and pick any point lying between these 2 points along the line segment joining them. Okay, denote that point by P, and then the point A0 is just opposite to this line segment joining A1 and A2, and we consider all such line segments as we keep varying P along this line segment joining A1 and A2. Okay, this way. So these are the points X. Okay, and this way we get all the points inside the triangular region. Okay, this is the figure. This is figure 1, and the name of this figure is 2 simplex. Okay, which is a triangle. Now we need to list some basic properties of simplices. Okay, I'm not going to the details of those properties. So the proof of those properties are left as as exercises at the end. Okay, I listed some exercises at the end, and you need to do the proofs there. Okay. Okay, so let me list the properties. So we'll study the properties without going over the proofs explicitly. Let us list some basic properties of simplices throughout. Let P be the plane determined by the points of the geometrically independent set, be the plane determined by the points of the geometrically independent set A0 all the way up to AN, and let sigma be the n simplex spanned by these points by these n plus 1 points. Okay, if if x is the point in this n simplex, let Ti of x, this set, be the barycentric coordinates of the point x. Okay. Right, so what does it mean? It means that you write x as a linear combination of all these n plus 1 points. Okay, and you want these scalars to satisfy this constraint. The sum of all these scalars is equal to 1 as I runs from 0 to n. Okay, so all right, so the following properties hold. One, the barycentric coordinate, coordinates Ti of x with respect to A0, A1, all the way up to AN, okay, are continuous functions. Functions of x. Okay. Well, these barycentric coordinates are uniquely determined by the given point x in the n simplex. Okay. Not only that, these coordinates are continuous functions of the points x. 2. Sigma that we have seen. So let me draw the picture again. We have seen earlier for the 2 simplex. So let us have this picture in the back of our mind while studying the general picture of general properties of an n simplex. So we had these 2 points A1 and A2, and we have the vertex A0 opposite to this line segment A1, A2, and there were these lines, right? That that fill up this triangular region. Okay. Now the second property tells us that sigma equals the simplex, the n simplex equals the union of all the line segments joining A0 to the points, okay, of the simplex S. Okay, so first of all, when we look at the picture of this triangular region, which is of course a two simplex, we see that when we look at this vertex A0, so there is a line opposite to this vertex A0, which is a one simplex, right? This is a one simplex. So we get this triangular region by taking the union of all these line segments, right? The ones that we have drawn here, okay? So, so these line segments are nothing but line segments joining A0 to points on this one simplex A1, A2, one simplex joining A1 and A2, one simplex, straight line. Okay, so we get line segments in general joining A0 to the points of the simplex S spanned by all the points except for A0. Here, in the two simplex case, all the points except for A0 are A1 and A2. A1 and A2. Okay, so if we just take off A0 from all the points, we are left with A1, A2 all the way up to AN. Okay, so we first need to form the simplex S spanned by all points except for A0, A1, A2 all the way up to AN, and then we have to take all the line segments joining A0 to the points of this n minus 1 simplex. This is this is an n minus 1 simplex, which is located opposite to A0. Okay. Two such line segments intersect only in the point A0. Okay, so if you pick up two such lines, okay, joining A0 to points on this one simplex, right? Then two such lines intersect only at this point A0 and nowhere else. Okay, so the same picture holds for an n simplex. Okay, good. So this was the second property. I think it's a good time to take a break, and we'll be back with the remaining properties of an n simplex in the second segment. Thank you for attending the first segment.